This video is over Chapter 8 of Statistics. We're going to learn about confidence intervals. Now this very directly ties in with where we left off in Chapter 6. So in Chapter 6 we were talking about the standard normal distribution. We were able to find the area in between any two given numbers. And then that very last section we learned how to go backwards and find out what area, so we learned out how to find what number a certain area would cut off. Something like that. So anyways, in the very first chapter, we kind of got a feel for these bell curves where we learned that one standard deviation out would cover 68% of the data. 2 was 95, 3 was 99.7. So this chapter, we found just how to find numbers other than 1, 2, and 3. And then that very last section, we said we could go backwards with that button in the calculator inverse norm. So we learned those 4 cases. We could find the inverse norm going to the left, which is what the calculator automatically did. We could trick it into going to the right because we knew that the area under the curve was always going to add to 1, so we just did 1 minus. The between was the trickiest one. We kind of had to reason through it in steps. And then the wings is something that didn't seem as practical because in all of our examples, the wings didn't really work out because we had 2 different numbers and stuff like that. So we never really got to try this one. But this is actually exactly what we needed for the confidence intervals. So in the wings right here, we could find whatever number would cut off a certain amount of area in those 2 tails. So in our confidence interval, we put it in kind of a more practical, everyday language, realistic sense. So we say those 2 numbers that we were able to find with that inverse norm cut off this such amount percent in the middle here. So we said that that percent in the middle is going to be between here and here. So in other words, we're basically 90% confident in this example that our data should fall between this number and this number. Now there's a little bit of technicality where, there's some wording if you get deep into the statistics where if you had repeated experiments and every single time you found the mean of those experiments, you're 90% confident that the mean would fall in between these 2 numbers. But more or less, it's not exactly the right terminology, but basically you could say something along the lines of you're 90% confident that a data's point should fall in this range. So that's kind of where we're going with all of this. That's why all of that stuff we learned last chapter is going to be a practical application. So again, keep that calculator handy. In this very first chapter, we go through kind of the more numerical calculations because I did want you to kind of connect it back to that chapter 6 stuff. But then after we get through some of the kind of like where are these numbers coming from, I teach you that magical button that does everything for you. So these first few are the only ones you'll have to really do a little bit more by hand, just the way that it's worded, you can't use the magic button. But then after we get that past this section, everything can be done with the magical button. So they put it in these funny terms right here, where just like you would expect, starting from the middle, we go up and down the same amount. Okay, so just like when we very first started with this kind of thing in chapter 1, when we learned about those empirical bell curves, we said we went 1, 2, and 3 standard deviations away from the center. So it's that same idea. So they just kind of give it some new names here. So the point estimate is the center. So that's going to be our sample mean because we expect our sample to be representative of the data. So remember, there's a little bit of kind of technicalityness going on here. So basically, point estimate is the mean. It's just saying that you don't know that it's the true population mean. It's just your sample mean. We go up and down a certain amount, but that certain amount is the same up and the same down, which makes sense, right? We want to go away from the middle. So they call that number that we go up and down the error, okay, hang on, which one of these do they call it? Point estimates, the middle, I didn't put it in here. Oh, here it is, the margin of error, sorry. So the maximum error of estimate. So with that amount we go up and down is that margin of error, the amount of wiggle room we're willing to give ourselves. And this forms the confidence interval. So the lower number, comma, the higher number, just like any interval notation, like you learned in college algebra. It's always the minimum, comma, the maximum. We always use the round parentheses instead of square brackets like we did in college algebra because we're not including those values. It's all estimates and, ifs and ishes and stuff like that. So we just use these round parentheses to say in this round area, but we don't use hard exactly here type numbers. So this gives us that confidence interval. Our interval estimate is the range of possible values for a population parameter. So we'd say we're such and such amount confident that the true population mean, if somehow we were able to find it, should be in here. So there's this kind of balancing act because of course you would want to be as confident as possible. So you'd want to be able to say you're 100% confident. But if you remember from chapter 1, that even right here, 3 standard deviations out, which is a pretty good amount of data, is only 99.7% confident. So to get 100% confidence is actually impossible because even though it gets really, 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 really skinny down here, it never actually touches the x-axis. You can never be 100% sure. There might be that one really extreme outlier in there. So because of that, we just want to kind of balance it, get as confident as we can. But the reason that sometimes we have to go a little bit less confident is because sometimes if we go too confident, it spreads our interval out so much that it becomes just something just bizarrely obvious. If you remember from our project that we did in class, we did that hair project, we found that confidence interval in class, and depending on which semester you guys take, a lot of times the lower bound ended up being in the negative. And we said that was because we had boy hair and girl hair mixed together, so we had a really large standard deviation. So again, it was just bizarrely obvious. Be like, oh, okay, well, obviously our hair range should fall between negative such and such, and then, that really high number that we got. So that is kind of the idea of going too confident. So in that case, especially with our high standard deviation, our range was something just, if you told somebody that, they would laugh at you. So in the next chapter, we take this and we build into a hypothesis test. So we take this confidence interval and we put it in the form of a question that we can answer. And that question, again, has to be reasonable. So you would say something like, I took a survey of the, we'll say hair length again, the hair length of all of the girls on campus, being more specific. And I'm 95% confident that everybody's hair length on campus is somewhere between -30 and 500 inches long. Well, you'd say, well, why did you even bother telling me that? I could have told you that without doing any sort of research. So that's kind of the balancing act. We have to get a confidence that people won't laugh at. You might say, I'm 30% confident that the hair length is here. And again, people would laugh at you. And you have to get numbers that are reasonable. So that's kind of the balancing act. So let's see what we can do with these numbers and make that happen. Okay, so these numbers right here are the more common levels of confidence. These numbers right here are the decimals that you would have gotten if you did your chapter 6, sorry, this one here, chapter 6, this one, inverse norms. Okay, so if you just kind of wanted to test your knowledge, you could take these numbers right here and find for this amount in between, okay, this was the between percent, which means this much was in the two wings, this much, or sorry, this right here would be the upper z-score that cuts that off. Okay, now remember when we found these in chapter 5, it automatically gave us the negative one, and we just said, okay, we know it's the negative and the positive. So that's what they did to find these numbers. They did the inverse norm of 1 minus that number, cut in half, and got these decimals. So you have them listed here. It's just kind of handy. Keep this nearby for this section of homework so you don't have to do an inverse norm for every single problem. Now it's possible that you would encounter one that's not in this list. What if they wanted to be 93% confident? Then you could just, from your chapter 6 knowledge, do an inverse norm for that amount between, just like we did last chapter. Okay, so remember that this gives you the z-score that cuts that off. Notice in the diagram here, here's that 1.645 that cuts off 90% in between. Okay, So the reason we need these numbers is this is known as the z-score of alpha over 2. Now the reason that it's listed as this kind of really weird variable right here is because they call alpha, okay, the amount in the tails, the amount of possible error, okay, that we're cutting off on the sides, which is 1 minus the level of confidence that we choose to have. Okay, they cut that in half, just like we did when we were doing that inverse norm, because half is in the lower tail and half is in the upper tail. So they give it this weird variable name, z of alpha over 2, as specifically the z-score that cuts off those two tails. So this right here is one variable, it's one thing. So when we use this formula that we're about to learn, this is going to be one single number. Okay, the mean amount of money spent on lunch per week for a sample of 75 students is $42. If the margin of error for the population mean with a 90% confidence interval is 2.10, construct a 90% confidence interval for the mean amount of money spent per week for all students spent on lunch. Okay, there we go. Now this one, they've done half of the work for us. We're going to learn how to find some of these numbers that they've given us, but we're just kind of getting started. So they found the mean. Okay, so they said they did this sample, 75 students were in the sample, and they found the average amount of money was $42. We're going to find the confidence interval after they've already found the margin of error. Now be careful, it says margin of error, blah, 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 is 210. So it's a little bit far away from the word. So that means we need to go both up and down $2.10 from the average. So 42 down 210, 42 up 210. I'm only doing it once. It's not the standard deviation. This is the margin of error, which is something we're going to learn how to calculate ourselves in just a little bit. Okay, so we're just creating the confidence interval by going from the norm, the 42, up and down by the same amount. It should give you 39.90 and 44.10. Okay, we usually list it as interval notation with the lower boundary, 39.90, comma, the upper boundary, 44.10. Now you could also list it as 39.9, that'd be fine. Just since it was money, I was putting it in money notation. Okay, and that's all they want. This is just kind of a warm-up problem. Like I said, they did most of the work for us. So we just needed to kind of piece together those last little bits of the mean combined with the margin of error. Okay, so let's take it a step further. So here's how they got that margin of error number that they just gave us in the last problem. Here, like I said, is that z of alpha over 2. This is one single number, which can usually be found right here in this chart. Like I said, in the rare case where you have a level of confidence that's not listed here, do it just like your z of alpha over 2 problems from chapter 6 for the between specifically. So that number that they give you, say it was 93%, we'd put right here. So we put a 0.93 right here. Okay, back over here. So this z of alpha over 2 is right here. Here's one single number, z of alpha over 2. Notice that they multiply him by the standard deviation, which should make sense. That's how much we spread out. Remember from chapter 1, we learned to go out from the mean by the standard deviation. But right here, here's what's affecting it slightly. The sample size. N is the size of the sample. Now, it makes sense if you think about it. So if I said I'm such and such amount sure, and I asked 5 people, would you believe me, as opposed to somebody else says, I'm such and such amount sure, and I asked 5,000 people? You'd probably have more confidence in that person, right? So it affects how confident you are based on how many people you asked. The more that you increase the sample size, the more you increase your confidence. So it affects the E that you have to go up and down from the mean. So we have our standard deviation, which should be obvious, and then also the sample size. Okay, now this right here, ask us for something else called the minimum sample size. Now this right here is this formula and or this formula, depending on the case, which we're going to talk about. Now these two right here are the one and only formulas that you'll have to follow in this whole Chapter, okay? Everything else we have a magical calculator button, but those are the only two. And notice that they both have that z of alpha over 2, which is one single number, okay? So you're not dividing it by 2. You're not doing anything. It's one single number, usually from that chart. But let's just try this one time real quick up here with these students eating their lunch. So if we had that 42 average and we wanted, let's say, they had the 90% confidence, then if we wanted to find that E using the formula that we just learned over there, we would have our z of alpha over 2, the standard deviation, and the square root of n. Okay? Now in this problem right here, they did not give us the standard deviation. Okay? So we couldn't actually find it by hand. But just as a silly example, just to kind of clarify my ramblings of the beginning, what if they had asked us to have a confidence level of 50%? We might have gotten a range of something like 40.0 to 40.8. And what if they'd asked us to have a confidence level of 99%? 99%. We might have had an answer of something like, I'm exaggerating here, -3 to 8 million, or we'll say 800,000. Sorry. Okay, there we go. So what does this mean? So in this one, they were 90% confident that if they grabbed any random student at the school, they probably would have spent roughly $39.90 to $44.10 on their lunch in a week, okay? So again, that's not technicality true, but this is basically what you could say. Now, if I said, somebody else came up and said, oh, I did the same survey, I'm 50% confident that somebody spent from $40 to $40.80. You say, oh, well, that's a lot more specific, but they're only 50% confidence. So you wouldn't really put a lot of stock in that. You'd say, well, then what is the other half of the class spending? So that wouldn't be a very good statement to make. Now, the other one, like I said, the other extreme, somebody might come up and say, hey, I did this survey and I'm 99% confident that one of these students spent anywhere from -$3 to $8 million. Again, you'd say, oh, that's just sillily obvious. So this person right here would have had the best information to give you. So they had a reasonable amount of confidence and their range was not too wide to be ridiculous. So that's kind of that balance. You want to have enough confidence to be, for anyone to even listen to you. And then you want it to have a range that's narrow enough to be practical, to have any sort of application. Okay. So this is how they got that margin of error. So knowing the standard deviation, you could have actually gone in and calculated it. But like I said, don't worry, you're never going to have to use this formula. Here's the only two you need. So here's that z of alpha over 2 in action. Here it gets some fun. So grab that calculator, you can play along. So this one is the minimum sample size. So like we were saying, the sample size affects how confident you can be. So if you only asked 5 people, you wouldn't have as much information to go by. Your confidence is going to get thrown out the window. If you ask 5,000 people, things are much better for you. So this right here is a formula to determine how confident you want to be and how narrow you want that range to be. So up here we said, this range was obviously too wide. People wouldn't even listen to him. This range is good. It's very narrow. This guy is very specific, but he's not confident enough. So if you pick those two things, how confident you want to be and how much you want to spread out to be, reliable, not just super obvious, then you can find out how many people you need to ask to make that happen. And that's the minimum sample size. Now, because it is the minimum sample size, you always have to round up. So highlight this, underline, circle, whatever you need, because you're always, always, always going to round these up because it is the minimum. If you go down, you have not achieved the minimum. So make sure you always, always, always round these up. Super important. All right, let's try it out. So this guy, he wants to know how many times per hour a certain strand of virus reproduces. He wants to be 99% confident. That's pretty confident. And he's only willing to accept a maximum error of 0.2. So that means if he goes above that, all of the fellow researchers are going to laugh at him, just like these guys would have laughed at us for saying this amount of money spent on lunch. So he says, okay, I got to do this, and I got to be this confident, or I'm going to get laughed at. So how many times do I need to run this experiment? So he's already found that the mean is 8.4, and the standard deviation is 2.4. What is the sample size he needs to take to make his life easier? So we're going to use this formula right here. I have a standard deviation, okay? Since I have a standard deviation, I use this formula. Notice this one's different. We're going to talk about that. So I go the z of alpha over 2. That's a number from the chart associated with this percentage. Okay, here's my chart. Here's the 99. Here is the z of alpha over 2. 2.57583. 2.57583. So you see why you want to have that handy. Okay, it's not something you really have memorized. Take all of those numbers. If you round that, you're going to get the wrong answer. Okay, that is going to be multiplied to the standard deviation, which is 2.4. Be careful, that is the standard deviation, not the variance, divided by the maximum error that he's willing to accept, 0.2. Okay, now listen to me now. To get this correct, you need to do this inside stuff first. Don't try to type it in all together. You will mess up. In your calculator right now with me, type this in. 2.57583 times 2.4 divided by 0.2, enter. Hit enter right there or you will get this wrong. So I put in 2.57583 times the 2.4 divided by the 2.2, enter. Do not skip this step. That should give you 30.90996. Do not round. And then square it. So make sure you hit enter, you get this number, and then you square it. Okay, now you should get 955.4 blah, blah, blah. But we always, always, always round it up. So we can't take 955.4 experiments, so we're going to take 956. Now, even though it was a 0.4, which would have rounded down, that would not have achieved the minimum because the minimum was 955.4. So if I didn't do that 0.4, I haven't reached the minimum, I would either get not as confident or I would get more error. So I have to do more than 956 if I want these two things to happen. Okay. All right. Now the next one here, we start out the same. I'm reading through, I've got the same information. I still have a level of confidence. I need to be 98% confident. But this time, notice, it doesn't have a standard deviation. Instead, it has these proportions. So what does this mean? The population proportion. So in this case, we've got a, it doesn't even really tell us much about what we're studying, but it says that it's going to happen roughly 39% of the time. So we've done some studying, we watched whatever it was that's going on happen, and we found that it happened 39% of the time. So it's obviously not this one. This is the proportions, okay? So this usually ends up in a case that's kind of binomial. It happened or it didn't happen, and we have the proportion of times that it did happen, which is known as P. So this right here is our P. So in our formula, notice we have a P and a Q. Well, Q is just the opposite of P. So once you know P, you find Q by saying 1 minus. Okay, because P plus Q should always add up to 1 whole. P is the proportion of times that it did happen. Q is the proportion of times that it didn't. So they should always add up to 1 whole. It did or it did not happen. So 1 minus P is Q or 1 minus Q is P. They always go together. So P and Q go together. Okay, so if this is P, they did not give us Q. they did give us the error. Notice that's still part of the formula up here. Okay, that's the error down there. Now, for some reason, don't overthink this. It's not 3 variables. I just had to get stuff from 2 different books. This is just the error right there. Okay. All right, so let's try this out. The first thing I need is Q to plug in the formula. So I go 1 minus 0.39, which gives me the other 61%, which is Q. Okay, 1 minus P is Q. Okay, all right, now I've got everything I need for my formula, so I start plugging in. Okay, N is the same Z of alpha over 2. Okay, this one's 98%. 98%, here's my Z of alpha over 2, 2.32635. 32635. 2.32635. Do not round or it will mess you up. Okay, notice that this one is squared, and then they multiply by the P, which was 0.39, and then they multiply by the Q, which was 0.61, and then they divide it by the error squared. So the error was, be careful, 3.5%. So it's 0.035. Okay, and that is also squared. Now, I'm going to tweak this formula for you to make your life just a little bit easier. Notice how this one's squared and this one is squared. So here's something you can do. So in your calculator, follow me now, type in that 2.32635 divided by 0.035. So far you should have 2.32635 divided by 0.035. Enter. That should give you 66.467. Square that. Okay, and now you've done this part here. So you should have 4417.88, blah, blah. Okay, now with that right there, take that times, I'm going to jot down this number so you can know you're following along, 88108. Take that times the P, which is the 0.39. So go times 0.39 times 0.61. Okay, and that should give you the decimal. Oops, I messed it up. 1051.01. Okay. Let's see, I did mine slightly differently. Yeah, okay. So even though it's very, very, very much just barely over 51, we always, always, always round up, okay, because we needed this thing to happen. Even if we go down the tiniest bit, we would either be less than confident or a little bit higher in our error. So I actually need 1052 to make this happen. Okay, so here are those steps again. Take these two numbers and divide, hit enter. Then square it, hit enter, and then multiply by the P and the Q. So up here, let's kind of adjust this formula to kind of help you do that in your calculator. So again, remember that this is just the error number, it's all together, and this is the one number from your chart. So instead, the easier formula, you would go the error number from your chart, Z of alpha over 2, the E, the error, which will always be given in the problem, and then square it, and then multiply by P, and then multiply by Q. Okay, so this is your adjusted formula right here. All right, let's try just a couple more. So I know it seems kind of weird, but as you get more, as you increase, it'll get better. So here's another one, reading through. Here's my maximum error. I know I need that. Here's the confidence level I want to have. They give me some extra numbers in here, but here's what I'm looking for, standard deviation. Okay, so remember they would either give me the standard deviation or the proportion. Now real quick, as you get higher into this chapter, there's going to be a bunch of problems that all start out the same. So remember back in algebra, if you had something like this, you knew right away what you needed to do. You were trying to solve for x, it was obvious, there was no question, you went straight to it. Now in these statistics problems, it's a little bit sneaky because as we get higher and higher, they always give you the same information. They gave you the mean, they gave you the standard deviation, so you have to read that question. So the very first thing you should do after we get past this section is read the question. What did they actually want? So it says right here, what is the minimum number of people? Now, right now, that's the only thing we're talking about, so it's obvious that's what we're going to do. But when we get into section B, they give you all of the same information, but the question will be different. So make sure that you read that question first before you start working. Minimum number of people is the one and only formula that you have to work. So we decided this one had a standard deviation, so we're going to be using this formula here, the one where we squared at the end. So that when we take the z of alpha over 2, for 0.85, looking at that chart there, we have 1.43953. Okay, that again is from this chart right here, 85%, 1.43953. Okay, we take that times the standard deviation, which was given as 1.4. And divided by the maximum error they're willing to accept, in this case of 0.07. Okay, do the multiplication and division first, hit enter, do not round. So type in exactly 1.43953 times 1.4 divided by 0.07. Be sure to watch those zeros, hit enter, and that should give you 28.7906. Do not round, 0.7906, and then square it. Do not try to do any less steps than that or you will mess up. Okay, that's going to give you 828 and some change, and it doesn't matter if it's a little change or a lot of change, we always, 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 always round up. So this one would be 829. Okay, you have to be very careful on these numbers right here. If you do any rounding, it will affect this because when you square it, a very tiny amount changes this right here. Squaring makes things a lot bigger. Okay, next one, again, sample size. Like I said, obvious in this section because that's all we've learned so far, but make sure you do read to that question before you get started. This one I see instead of standard deviations, I've got population proportions. So I'm going to use that other formula. Remember, our kind of shortened version of the formula was to take the z of alpha over 2. Here's one we don't know. We get to practice that, okay? But we're going to put it right here. Divided by the error. Okay, that one is, oh, this is the sneaky one. Okay, they didn't give us the error, so we're going to check on that. And then this was our, oh, no, here it is. 4%, that's the error. 4%, but this is the one where they don't give us the population proportion, so we're going to talk about that. Now we're going to do this problem 2 times. The first time we want to be 98% confident, which is on our chart. That is the 1.95996. Okay, remember I find that division, I square it, and then I multiply by P and Q. And then we'll do it again for this one that's not on our chart. Okay, so I can show you how to get that. Now right here, a P and a Q. Now, in our formula, we decided that the P and the Q always added up to 1. In this example here, our P was 39% and our Q was 61%. So we were able to plug those in and get the answer. But in this one, we didn't know the P and the Q. So, Oh, we did. Sorry, it's the next one. Ah, I'm just getting excited. Okay, the next problem's even more fun. This one we know the population proportion. Okay, this one's less exciting. So this one is 0.86, and then the Q is 1 minus that. Okay, now remember that the Q is 1 minus that. It should be 0.14. Okay, so when I punch that in, remember to do the division, then square it, and then do this multiplication. That's going to give you, I'm going to put the number up here. So you do your 1.95996 and then divide that by 0.04. Should give you 48.999. Don't round, I know it's tempting. And then square that. And then take that times 0.86 times 0.14. That's going to give you 289 and just a tiny bit of change, but no matter what, we always round it up to the final minimum sample size of 290. Okay, now we're going to do the same exact problem with this amount of error. So this was for confidence, sorry, this was for 98% confidence. We're going to do the same exact problem for 97.5% confidence. Put it here. Okay. All right, so it's not on our chart. What do we do? Panic. No, don't panic. Okay, so we use our knowledge from last chapter. So we're going to go with our inverse vars, our second vars, because we need the inverse norm. So do second vars. The third option there is that inverse norm. Remember, this is the between one, so we have to do all that tweaking. So I go parentheses, open parentheses, 1 minus 0.975, close parentheses, divided by 2. Okay, so again, parentheses, 1 minus 0.975, close parentheses, divided by 2. Now for the z, z is for the standard. So even though this one right here might have a mean and standard deviation, I'm going to use the 0 and 1 because the z is specific to the standard deviation. No, the standard normal bell curve. Sorry. So I have to use 0, 1, even if the story has something else. It's because the z specifically is for the standard normal bell curve. This number is for standard. Okay, I hit enter, and that should give you a negative 2.2414. Take it to at least 5 places, just like all of mine here, at least 5. You can go more if you want. That would round right here to 2414, and that would even be a 0. Okay, now remember when I'm punching it in here, I was using the positive. You don't have to worry about it too much because it always gets squared and works itself out. But if you're just looking for a little more simplicity, you're only typing the positive one in. So I'm going to type in the 2.24140 because I always need at least 5 places or it will mess up. Okay, divided by same error times the same P and the same Q. Okay, this one is going to be, should get 56, and then you square that. And then we times by the 0.86 and times by the 0.14. Yep, okay. So that gives me 378 and some change. Again, just a teeny tiny bit of change, but it doesn't matter. We always round it up. So the final answer would be 379. So the reason that we did these two side by side is so you can see how very much this tiny bit of confidence affects things and why it's so important to round up. Because even this very small change in confidence right here, 97.5 to 98% confidence, you can see how drastically it affected the sample size. So to be even that tiny bit more confident, we had to ask, hang on, this seems wrong. I think something's wrong in my numbers here. Did I find the right number from the chart? I did not. This number's wrong in my chart. Hang on. Let me check this number. I grabbed the wrong line. I was doing 95% confidence. So I need this one right here, which is 2.32635. So I knew that something was off because to increase confidence would have needed to ask more people. So I knew that this was off. So this right here, I was off by a line and I got the wrong number. So it's going to affect these guys right here. Okay. So just a quick example that we all make mistakes and we got to be really careful. So you can see I was just getting in a hurry, read off the wrong line of the notes there and messed up the whole problem. But don't worry, it was an easy fix. So I just had to go in and tweak it. So whenever you do make a mistake, you can just kind of see where to kind of look for your small errors. So this one I grabbed the wrong line. That should have been 2.32635, which I actually had right up there, didn't I? 2.23635. Okay, and now when I punch that in, 2.23635 divided by the 0.04, that gives me 55.9. Again, don't round, it's tempting. Square that number. That should give you 3125.788, blah, blah. Take that in your calculator times 0.86 times 0.14. And that gives you 376.34, which means this one would need 377. That still doesn't seem right. What's going on? Guys, I just can't get this number right. Okay, I transposed those numbers, so be very careful. See, I'm just getting in a hurry, so keep this handy. It was 32635. I did 23. 32635. 32635. Okay, slow and steady wins the race. Okay, don't get in a hurry like me. Let's try it one more time. 2.32635 divided by 0.04. Then you square it. Should give you 3382, and then times 0.86 and times 0.14. All right, here we go. Hopefully this is the right one. Goodness. Okay, so this gives me 407.24, but it doesn't matter because I'm going to round it up to 408. So now I can finally explain this thing. So even though we only increased by 0.5% of confidence, it was a very small amount. You can see I needed to ask a whole nother like almost 30 people to get that confidence. So this confidence level is very specific. So you have to be very careful, and that's why we always have to round it up, because even that small change can throw things off by quite a bit, by a pretty drastic amount. So this one right here, when we only wanted 97.5% confidence, we had to ask 379 people. To increase by only 0.5%, I needed to ask 30 more people to get that level of confidence. So it's just very, very specific. Okay, so the last one that I was all excited about to show you. Here we go. So this time, we've got the margin of error. They want the sample size. Okay. They want us to be 95% confident, which I know very well now because that was the number I accidentally used last time. And they give us a percentage of people, but they didn't tell us the percentage of people. So here's the trick. Okay, we're going to try this out a couple times. So I know that the sample size formula that I'm going to need is the population proportion, which has the number from the chart for 95 1.95996. 1.95996. Double check that. 1.95996. Okay, be very careful. Divided by the amount of error they're willing to take, 1.5%. Make sure to write it as a percent. Make sure that you don't accidentally do 15%. 0.015 is 1.5%. That is going to get squared, but here is the mystery. What is my P and Q? So we're going to try this out a couple of times. So over here, I'm going to do the sample size for a P of 0.1 and a Q of 0.9. Okay, because remember they always add up to 1. And then I'll try it for 0.2, which of course would give me a Q of 0.8. 0.3 and 0.7. 0.4 and 0.6 and 0.5 and 0.5. Now don't worry, it's not going to take as long as it sounds like. There are, of course, every number in between here, but you should get the idea that we're trying to come across from these 5 numbers right here. So if this was my P and this was my Q, move this down just a little bit so we can label this. There we go. I've got everything covered, because if I went up any higher, I'd get 0.6, 0.4, and all we're going to do with these is multiply them. So P times Q. So right here, if I did this P and this Q, I would go 0.1 times 0.9. Well, what is that? What is 0.1 times 0.9? That gives me 0.09. So my PQ, my P times Q that would have gone into the formula would be 0.09. Let's try 0.2 times 0.8. That gives me 0.16. Okay, 0.3 times 0.7 gives me 0.21. 0.4 times 0.6 is 0.24. And last, 0.5 times 0.5 is 0.25. Okay, so remember, in this formula, every time right here, I would be multiplying by PQ. Okay, so let's try these out just really quickly. So in my calculator, I type in what I know for sure, 1.95996, very careful, divided by 0.015, not 15, be careful, watch that 0, and then I square it. Okay, so keep that crazy number right there in your calculator, 17073, 17,073.0809. So this part here gives you 17073.0809. This is what would need to be multiplied by this PQ. Okay, so take that number in your calculator times 0.09. Okay, should get 1536, which would round up to 1537. Okay, so delete that and do the 17073 times 0.16. And round that up, that would give you 2732. Okay, so this is your minimum sample size in. Okay, let's try it for the 0.21. So delete that, take your 17073 and times it by 0.21. It gives you, rounded up to 3586. Don't worry, we're almost there. Okay, 2 more times. Take that number times the 0.24. Gives you 4098. And one last time, delete that and then take it times 0.25. And that rounds us up to 4269. Okay. All right, now remember, this was the minimum sample size. So if we wanted for sure to be this confident, no matter what, we need the minimum, okay? This number has to be the bottom for us to achieve this level of confidence. So no matter what the P and Q are, if we needed the minimum to for sure be this confident, the biggest number, okay? I know it seems a little backwards, but think about it. The biggest number is the one that's going to get me there. Okay, so I know for sure if I ask 4,269 people, no matter what's going on with P and Q, I'm going to get this level of confidence. Okay, if I ask any less, it would depend on if my P and Q were good, but this is the very biggest number. If I ask this one, I know for sure that I'm that confident. So they have this special formula that if you ever don't know P and Q, which a lot of times we don't, remember this is the population, we don't always know a lot about the population, that you automatically use a P and a Q of 0.0 or 0.5 right here, because those are the ones that are going to create the biggest minimum. Okay, they're going to make sure that you're there no matter what's going on here. So that's kind of a special formula, a special case. If you ever don't know P and Q, you're going to use 0.5. Okay, so if you're ever unsure, use 0.5, 0.5. Okay, so anytime that it's unknown. So the answer to this problem is the one we circled down here, the biggest one, because we multiplied it by 0.5 times 0.5. That was the biggest one we could do. Because remember, if I kept going down the list, I'd get 0.6, 0.4. 0.6 times 0.4 is the exact same 0.24. So that's why if it's ever unknown, we use these two specifically because they make the biggest minimum. Okay? All right, so I know it seems like some weird stuff, but it's all, like I said, exactly specifically related to what we just finished. We're just taking it to a more practical level. So the next section we'll learn how to find those confidence intervals. Make sure you do have that calculator because there's a magical button that does almost all of the rest of the work in this chapter for you.